Hello, and welcome to lecture number 3 on chapter 4, your final lecture on 2 and 3-dimensional simple kinematics. Now, to begin today's lecture, I would like to introduce the concept of something called uniform circular motion. So, uniform circular motion. Now, uniform circular motion is an example of something called simple harmonic motion. Examples of things that exhibit simple harmonic motion: orbits, spring motion, pendula, like in a grandfather clock or something like that. And one of the things that makes simple harmonic motion so important is that many things can be modeled using it. So, that said, the first example of it that you typically see is what happens when something goes around in a circle at a constant speed. Now, so in order for there to be uniform circular motion, you have to have a constant speed and the radius and length is constant. So, what that does is to make whatever it is that you're looking at go around in a circle. So, here's a circle, something like that. And just to sort of label things, because we're going to be dealing a lot with them today. Let's draw us a little coordinate system. This is y, this is x. Maybe you have a rock being swung around a string, close to circular orbit, something like that. And you would locate the orbit using a radius vector. So this would be r vector, like that. Now, as this thing goes around at any given time, if you stopped its motion and you looked at the direction that it was heading in, what you would notice is that it would be at right angles to its location. So this is your velocity vector v. Okay. Now, so what I'd like to do is to derive the acceleration felt by this thing as it goes around. Now, I want you to remember that, and we're going to use the average acceleration version of this just momentarily, that acceleration looks something like how your position changes over time. Okay, remember, it's a derivative. Now, so keeping this in mind, and also keeping in mind the following relationship from trig: the length of an arc along a circle is equal to the radius of the circle times the angle that's swept out. We're going to derive a relationship for acceleration in this particular case. So I want you to imagine, and let me shift to another sheet over here. I want to make a big old circle like this for illustrative purposes. And let me cut it in half. I think somewhere around over here is where x would be, and then somewhere around over here was where y would be, like that. So imagine your planet or rock or whatever it is going around in a circle with an initial position like that. So here's your thing. That's a right angle. This would be its initial velocity, and this would be its initial position. Now, to be very, very clear, the speed, that is the magnitude of the velocity, is constant. But the vector velocity is not constant. Why is that? Well, as this thing goes around, the direction is continually changing. And remember, vectors have magnitudes and direction. So even though the speed itself may not change, the direction is continuously changing. And what that means is that your vector is not a constant vector, even though its magnitude is. So here's the initial position of your thing as it goes around in a circle. And then later on, maybe here, your thing, oops, never works out the way I want it to when I do that. Is going this way. All right. Now, there's your right angle. This would be your new R. This would be your new V. So you initially start here, you finally end up here. Now this right here would be the change in angle, the change in theta that you experience going from here to here. All right. Now, so let me just take the R part here, dealing with R and R naught, and I'm going to draw that out sort of as a wedge like this. So maybe if you think about this thing moving along a path that looks like this. So there's S, right? That's a pretty good arc. This would be R naught, and this would be R. And this right here would be the angle swept out d theta. This would be the change in R. Okay, if you remember our conversation 2 lectures ago, where I introduced some of the concepts dealing with 2 and 3-dimensional vectors and displacement, this right here would be dr, or delta r vector. Now, in terms of lengths, remember the magnitude of our radius does not change. It's on a circle. What happens is the direction as this thing goes around changes. So r itself in magnitude may be constant, but because it's directional, it's not constant, okay, as a vector. So this right here, like I said, would be delta r, or we're going to call it dr, just in magnitude. So let's see, if you remember over here where I said, let's not forget this, S is equal to R theta, then if you were to look, we'll say at S is equal to R theta, and take the differential of both sides, ds. R is constant, remember, like that. Well, here, S is the thing that's being swept out, and if this angle is very small, d theta is small, then that would be the same thing as dr. So as you can see here, dr, which would be the length of S, is equal to r times d theta. Okay, see? Same thing. Now, I want to take a look at the velocity here. So initially, you end up here, or you start here rather, you end up here. Okay, there's your final position. Your velocity and length does not change, much like the radius vector. What happens is the direction changes. And you'll notice that these things, again, are linked by 90 degrees. So r points this way, v is perpendicular to it. R points this way, v is perpendicular to it. Now, what that means is that if you took a look at the angle that was swept out as V naught went from pointing this way to pointing this way, it would be the same angle that's swept out by this. The way to think about it would be kind of like this. If I drew a vector that looked like V naught like that, so there's a duplicate of it. And let's see. Actually, I'll tell you what. Let me redraw that. I want to draw it over here so I can move it. So there's V naught. It looks something like that. If I were to still this thing right here and then move it like that, okay. This right here, whoops. This right here would be the same angle here. This would be d theta. Now the lengths would be the same. They aren't in this case because I freehanded this. But basically, if you take a look at the direction of, if this is V naught and this is V, then it would be true that this right here would be delta V. So let's take this and sort of replicate it down here. I'm going to try to maintain sort of a similar alignment like that. Okay. So V naught points this way, V points this way. This is the same angle. Okay. And again, if you deal with small angles, then this right here would be the same thing as dV. Keeping in mind that V naught and V are the same in magnitude, as the direction is different. And using the same thought process as looking at the relationship between arcs and stuff like that, then as you can see here, dV would be the same thing as ds conceptually. R would just be V in magnitude, and then d theta. Okay, so this is a true statement right here. This is a true statement right here. So that said, let me scroll down here just a touch. And now from looking at arguments dealing with the direction of the radius vector, we get this. From looking at arguments dealing with the direction of the velocity vector, since the radius and the velocity are linked by 90 degrees, you have the same angle being swept out. And remember, the magnitude of your velocity, that is your speed, is constant. The radius is constant. Okay? So let's not forget that. If I were to take and divide both sides by dt, noting the fact that v by itself is constant and r by itself is constant, the angle, though, does change in time as this goes around. And so does the location of r and the location of v. Then what I have here, because dr dt is v, is something that looks like this. Now I'm going to call omega. It looks like a W, it's not. D theta dt. This is angular velocity, sometimes called angular speed, or not angular speed, but angular frequency. Okay? And what it does, or what it is rather, in uniform circular motion is, on average, one full orbit through an angle over how long it takes for you to do that. Okay, now we're going to come back to exactly what that means here in a second. But I don't want us to forget that this is how we have defined it. That is our angular velocity. Okay, so this is omega, and this is omega. So dr dt, which is your speed, is equal to r times omega. And dv dt, which is acceleration, is equal to v times omega. Now, let's talk about the direction of your acceleration. If you start in this direction and you end up in this direction, your acceleration is in towards the center of the circle. Okay, actually dead towards the center as it goes around. It goes like this. Whoops, not that way. That way, like that. Now, so this has a technical name. This is called centripetal acceleration. That is in towards the center. Acceleration. And that's what this is. So to denote it as that, I'm going to call it A sub CP. Now, we're going to take these two equations, and let me name them first. This right here would be the equation for something called tangential velocity. This is also the equation for centripetal acceleration. Oops. Centripetal acceleration. So V over R is equal to omega. A over V is equal to omega, meaning that V over R and A over V are equivalent. So if I solve for A here, A is V squared over R. And this is the conventional way that you see it written. All right, now, so let's take just a brief step back and look at tangential velocity. If I knew the radius of my circle here, and I knew how quickly I swept out angles over time, I could tell you how quickly I was traveling. I would tell you my speed. That's what this is. Tangential velocity is your velocity along this direction right here. Okay? If I knew what my velocity was, and I knew how quickly I swept out angles over time, that is my angular velocity or my angular frequency, I could tell you the centripetal acceleration. But using both of these equations says that I don't need to know anything about angles. All I need to know really is about speed and about the radius of the circle. Okay. Now, so that said, let me work a couple of simple examples here. You have a person that exits the interstate using an off-ramp that has a radius of curvature of 400 meters. If the car maintains a constant speed of 70 miles per hour, what centripetal acceleration does it experience? Okay, so I want you to imagine that this right here would be our interstate like that. And when you exit off of the interstate and you look at the shape of an off-ramp or an on-ramp, they have this arc look to them. And that's because exit ramps or entrance ramps are typically based off of sections of circles. So when you say that the off-ramp has a radius of curvature of 400 meters. What that means is that if you were to look at the part that has an arc to it and complete the circle, like for example, like this. Oops. Now let me get my eraser out here. So this right here, for example, might be what your exit looks like. So you see how this is based off of the section of a circle? So here, if you were to look at the radius of that circle, it would be whatever the radius of the circle was that I had here before, which would be something like this. That would be the center. And this is your radius of curvature. Okay. Now, your car, when it exits, we're going to have exit at a constant speed. Okay. So your speed here is 70 miles per hour. We're going to obviously need to convert that. But it maintains 70 as it goes. But look at the direction. Here, for example, it's going something like that. Here it's going this way. Here it's going this way. Here it's going this way. So as you can see, the direction of your velocity continually changes, even though your speed does not. Again, this is uniform circular motion. The velocity vector is not constant, but the magnitude is. So here, we're given that the speed is 70 miles per hour. We're also given that the radius of curvature of your exit is 400 meters. Now let's take your speed and do a quick conversion. Let's see here. If I convert that, I get something like 31.29 meters per second. And really all we're asking for is what acceleration this car would need to experience to stay along the arc here as it goes. Now, what's producing this acceleration? Well, we haven't really gotten into that yet because we haven't talked about forces. That's the subject of the next chapter. But I can tell you that it's related to the friction between the tires and the ground. Okay? That's what keeps you on this path. Now, however, if you think about what you feel when you go around the corner like this, you, instead of feeling like you're experiencing acceleration inwards, you feel like you're being thrown outwards, right? That's due to something called inertia, which we're going to be talking about starting next lecture. So that said, here, the acceleration that this car would need to stay on the path, not the acceleration that it might experience as it, zings through the curve like this, but the acceleration that's inwards here that maintains the circular path is going to look like this. And in this case, that would be 31.29 meters per second squared divided by 400 meters. So if you do that, I get an acceleration of about 2.45 meters per second squared. This is the magnitude. It's obviously inwards. And so I see one sig fig here, one sig fig here, which means that this is about 2 meters per second squared. So there's your answer right there. Now let's work another one. So in this one, we're going to look at the orbit of the Earth around the sun. It turns out that if you look at the shapes of the orbits of the planets, they're ellipses, but a circle is a special case of an ellipse, and the Earth's ellipse is almost a perfect circle. So, that said, let's draw a picture. Here's the path of the orbit of the Earth around the sun. Let's draw some coordinates like this and like this. This is the y direction. This is the x direction. I guess I must have forgotten to take the, there we go. It turned out pretty well. Now let's label some stuff. We'll say here's the location of the Earth in its orbit right now. Maybe here. The length of the orbit, its radius, is 1.5 times 10 to the 11th meters. This is actually called an astronomical unit. It's used in astronomy. Now, so we actually also know a few other things. For example, will you agree with me that when something goes around a circle once, that the angle that it sweeps out is 2 pi radians? Well, yeah. Now, that said, here's some terminology. When something goes around in a circle, or something swings one full swing, or something oscillates back and forth once, we call that behavior, that over and over and over and over, repeatable, consistently the same behavior, periodic motion. So the amount of time it takes for something to go around once, or for the pendulum of a clock to swing back and forth once, or for a spring to bounce through an oscillation once, is called a period. It's the time for one complete oscillation. Okay? So for the Earth, we know that its period, which we're going to denote by capital T, is 1 year, or 365 days, or however many seconds that is, which we're actually going to calculate. So if you think back here, when I was talking about angular velocity, the angular velocity of the Earth would be one orbit through its angles, 2 pi, over however long it takes for it to do that. Velocity is distance, or speed is distance over time, rather. That's what this is basically, is a speed. Okay? So omega we could find by looking at 2 pi over t. And we're going to do that. Okay? But that said, before we get too far ahead of ourselves, I'd like to point out that that's additional information that we know. So we're given that it takes 1 year, or 365 days, or 365 days, there are 24 hours for every 1 day. And there are 3,600 seconds for every 1 hour. This many seconds. Let's go ahead and do that. Actually 31,536,000. So I'm going to write the full number out. This is how many seconds are in a year. Okay. We also know that the length of this orbit, its radius, is 1.5 times 10 to the 11th meters. Now, what are we trying to find? The average speed v, the angular speed omega, and the centripetal acceleration that it experiences, a sub cp. So we have a couple of routes to doing this. If you look over here, though, we have tangential velocity, which would be its speed in its orbit. And we have another way of expressing centripetal acceleration. But here, if you look, the way our centripetal acceleration is being expressed, and the way that our tangential velocity is being expressed is it depends upon omega. So I propose that we use those forms. We know V is R omega, and we know A sub Cp is V omega. All right. So omega here is going to be 2 pi over the period. It goes 2 pi radians for every 31,536,000 seconds. So 2 times pi divided by something like 1.99 times 10 to the minus 7th 1 over seconds. Now, this is the reason why angular velocity is sometimes called angular frequency. 1 over seconds, those units, sometimes are called the hertz, and they deal with frequency. We'll be talking about that later on. That's not really a subject to get into yet. That said, though, knowing this, we have the tools that we need in order to find the rest of the stuff. Our tangential velocity, which is the speed this thing has as it goes around the circle, is r times omega. 1.5 times 10 to the 11th meters times 1.99 times 10 to the minus 7th radians per second. It's technically the unit for that. If you do this, you get do my calculation here. $29,884 meters per second, or keeping to 2 sig figs, 30 kilometers per second. That's how fast the Earth goes around the sun. Now, what centripetal acceleration does it experience? Well, you'd think, considering the Earth is so massive and the sun is so massive, that it would be a lot. But let's see. That would be V times omega, or 29,884 meters per second times 1.99 times 10 to the minus 7th radians per second. And if you do that, It ends up being 5.9 times 10 to the minus third meters per second squared. Very small. So there's the acceleration that the Earth experiences as it goes around the sun. And this is its velocity. And this right here is its angular acceleration. Or not its angular acceleration, its angular velocity. Now, that said, what I would like to do is to use uniform circular motion as a foundation to go back and look at velocity, acceleration, and position as vectors. And the reason why is because this gives us a very obvious example of places in which the acceleration can change continuously. So, that said, I want you to consider something going around again in a circle at a constant rate. A rock on a string, again, something like the Earth. Really doesn't matter, just something. Okay, now, so I'm going to locate that something right here. Here it is, right here. And this is the angle that's being swept out as this thing goes around this way, we'll say. So there's the direction of the velocity like that. It's going around like that. Now, so here's our position vector r. And r, we know you can write from a unit vector standpoint as having an x position and a y position, right? Now, that said, if you think about opposites, adjacents, and hypotenuses, here, and let's just sort of illustrate the point here. Okay, so this right here would be y, and this right here would be x, right, in terms of this stuff over here. And so we know, for example, sine of theta is opposite over hypotenuse. The length of the r vector is just r, the radius. So here, opposite over hypotenuse would be y over r. Adjacent over hypotenuse would be x over r. And if you solve for y, that's the same thing as r times sine of theta. If you solve for x, that would be the same thing as r times cosine of theta. So another way that you could write r in terms of things like radiuses and stuff like that, which are more natural when it comes to things moving along a circle, because they form the basis of something called polar coordinates or circular polar coordinates. Here would be r times cosine of theta in the x direction plus r times sine of theta in the y direction. Now, so let's talk more about where the time relationship is here, because we're going to end up taking some derivatives. And I'd like to look specifically at our angle. You see, the length of our vector r doesn't change. X and y as unit vectors do not change. They always point along the x direction or along the y direction. Now, what's forcing the change here is the fact that this thing is moving through an angle over time. That means it has an angular velocity. So if you go back over here, where we had defined angular velocity as omega being d theta dt, let's see here, go back. What that means is that you can write down your omega as d theta dt. So what you've done is you've taken the derivative of theta, with respect to time, and you've got an omega. Now, with uniform circular motion like this, omega is constant. Now, at this point, you should have had enough differential calculus to note that if you take the derivative of something and you get a constant, originally what you had was a constant times a time, or a time raised to some power, that is, the first power. Now, so what I'm saying here is that the relationship between theta, omega, and t looks a lot like the relationship between velocity, changes in position, and changes in time. So much so that you can express theta as being omega times t. Now, when you get to the point in calculus to where you can do integral calculus, you'll see exactly what I'm talking about. But this is where the link through time is. Theta is omega times t. So another way that you can write your position vector here is that it's r times cosine of omega times t in the x-hat direction plus r times cosine times omega times t in the y-hat direction. Okay? So what that means is that given our position as a function of time, we can appeal to all of those generalizations that we used to find things like velocity and acceleration. So, for example, I know the velocity of a vector is the derivative of its position with respect to time, which would be the same thing as taking the derivative with respect to time of r cosine omega t x hat plus r times sine omega t y hat. Now, r is constant. It's the length of this motion. And since we're dealing with uniform circular motion, remember the radius is a constant thing. Omega is constant. X hat is constant. The only thing that we have is this time that's changing inside this trig function. So, if I remember correctly, the derivative of sine with respect to something, the derivative of sine is cosine. And the derivative of cosine is minus sine. Right? Now we have this added chain rule that we have to do. You take the derivative of sine and then you take the derivative of what's on the inside. And if you take the derivative, for example, of omega t by t, you get omega. Okay. So here, for example, if I took the derivative with respect to time of r cosine omega times t, the r comes out, and what I'm taking is the derivative of this. Now, when you use the chain rule here, the derivative of cosine is minus sine. But you still have to take the derivative of what was on the inside, which we did here. It's omega. So for this right here, it's minus r times omega sine omega t. If you take the derivative with respect to time of r sine omega t, following the same process, the r comes out, you're taking the derivative with respect to time of sine of omega t. The derivative of sine is cosine. The omega comes out. So what you have here, When you take your derivative here, noting the fact that much like this r, x hat and y hat are constants, the velocity that you get is going to look like minus r omega sine omega t x hat plus r omega cosine omega t. Or what am I doing here? Yeah, cosine omega t y hat. There we go. So take a look at what this means. The direction that we have here for v, for r is just the first quadrant right here is positive x, positive y. This is minus x, positive y, which means that if we were to go up here and look, minus x, positive y gives you a velocity that's in this direction. It's tangential, like I had said. Now, furthermore, we can find the acceleration. It's the derivative of your velocity with respect to time, or two derivatives of your position with respect to time. Well, following the same process here, if I take and do d by dt of minus r omega sine omega t x hat plus r omega cosine of omega t y hat. The r's and the omegas are common between these two, and I can just pull them out. They're constants. Okay, so once again, derivative of sine is cosine. The derivative of cosine is minus sine. You have an omega on the inside to the chain rule that you can pull out. And this is an important result right here, because look what it's telling us. So this is a vector. This is your acceleration vector, right? You see how there's a minus sign in front of both of these terms because of the way sines and cosines oscillate when you take two derivatives. Let's pull that minus sign out for a moment. I'd like to compare this to r. This is just the location up here. R cosine omega t plus what this is all about. This should be a sine. Sorry about that. It's the same. So you see this, if I pull this r into there, this is just the r vector, like that. Okay, but there's a minus sign. And if you remember chapter 2, when we talked about what happens when you multiply a vector by a negative scalar, it reverses the direction. So what that tells us here is that graphically, you're locating your thing this way, but the acceleration is straight down r this way. So this would be the direction of your acceleration. So this is as far as I'm going to take this example. I just wanted to show you that you can actually use these things to find out, velocities and accelerations and stuff like that. Now, one of the things we're not going to do at this moment is to use the Pythagorean theorem to show that the length of v and the length of a look exactly like, this here. But I encourage you to do it. Okay, so this is a bridge. This just shows you how it's used. Now we're gonna appeal more and more to this as the class goes on, but not quite yet. We need to build up the foundation first. And that concludes the third and final lecture for Chapter 4.